This is the podcast of the activity of designing compensators. This is my team, and for the subject of control engineering. Okay, for the first thing we need to know is that we have this transfer function, and we modify it in order to eliminate this factor. So the transfer function is like this now. Then we were asked to design a compensator so that the system does not have a steady state error, and the stabilization time is 2% of 0.25 seconds, and it we need to contemplate an overshoot of approximately 10%. So the first thing that we do is we calculate the sigma with the this data of the 0.25 seconds, um, and we obtain that it is 16. Then for the overshoot we were asked to be like 10%. We have this formula, and we just uh, isolate zeta, and then we obtain this value 0.5911. With that value we are able now to calculate theta. We calculate that, and then omega n. Omega n is just sigma over zeta, and then with omega n we are able to calculate omega d. So we were asked to consider no steady state error, so it could be type 1 or type 2. But since type 1 is easier, we chose that. So this would be our representation of the transfer function, and we know that if we use a PID compensator, we would add 2 zeros and 1 pole. So one of the zeros that we add cancels out with the pole of this term. So now we have the formula of the KP, and we use the departure angle formula in order to then, with the contributions that we obtain, we can achieve the arrival angle required from this desired pole to this 0. So then we can calculate the the distance between the overlap pole and 0 to the new 0 that we are adding. So that distance would be omega d over the tangent of the arrival angle that we calculated before. So we obtain this value of distance. So if we need to know where we will add that 0, we just need to add sigma to the value that we obtain of distance, that is this one. So the new 0 that we add is on 22.8 from the origin. Then for the PID compensator, we know that we have some constant that is the absolute value of the pole of the distance in which was the first pole, and another constant that is the total distance from the origin to the new 0. So for calculating Ti and Td, we have this multiplication of the constants and this summation of the constant. So now we have the formula of our compensator, and we need to remember that this uh, formula is very important because we will use it later on. And we calculate TD with this formula, and TI. So we have the multiplication of chi I times the compensator times the plant, and then we just evaluate on that multiplication the value of S, that is sigma plus omega d, and that would be equal to 1. We forced it to be equal to 1. So we perform some algebra and substitutions, and then we got that Ki is equal to 0.88 almost. So then we can calculate Kp with the formula above that I mentioned before. So Kp is equal to Ki over Td, and then we know that Kp, the proportional value, is 23.9. So now the final compensator, uh, multiplicating the plant, is like this, and then just performing the multiplication, we can get the new transfer function, that is the modified transfer function, and it is like this. So then we can sketch this in MATLAB uh, with the new uh, the new parameters, and we can make uh, a plot like this. So now this is the compensated transfer function, and for the part of the R locus, we were asked also to perform that in MATLAB. So we just write R locus of the transfer function, and we got this figure of the R locus, the Pokeball. The next step is defining a prefilter, and this is very simple. We just need to know the coordinate of the new zero that we obtained with the arrival angles and that stuff, and we just define a new transfer function, a little one, that is defined by c over s plus c, being c as the coordinate that I mentioned before. And we know that this coordinate c is equal to 22.8 because of the actions we performed before. Okay, so our prefilter is defined like this. We have this prefilter. We declare it in here, but this thing I will show you later. Okay, so the next step is to obtain the transfer function of the system. We have the output and the input. We perform some operations just to eliminate this fraction in s, and we equal the system to this one, to this thing. And we have the state variables and the derivative of the state variables, and we obtain the relationship between them with some parameters that are filled in the matrix A and B, that we will use them later. And we also have the output, the output matrix that tells you what which of the state space variables is the output. So now we can achieve the controllability of the system just by concatenating or adding some matrices. The first one is B, and the second one is A times B, and this will repeat until the multiplicity of A times B is n minus 1, being n the number of state variables that in this case is 2 variables. So the multiplication between A and B will be once only. Okay, so we obtain the determinant of this new matrix alpha, yes, and we obtain this. And since it is not equal to 0, we can say that the system is controllable because it's different, and the rank of this matrix is equal to the state variables of the system, that in this case is 2. For the observability, we just concatenate again some matrices, but in this way, not in this way. So we perform the multiplication of the matrices C times A, again with the condition of the multiplicity n minus 1. So we just perform once the multiplication of C times A. Okay, so we obtain that the determinant is 1, so it's different to 0, and we obtain that this system is observable, and the rank is equal to 2. So the next step is to perform the controllability law, and this is obtained by making equal the desired poles, the initial poles that we obtain with sigma and omega d, sigma and omega d, and is equal to the determinant of these matrices, the identity matrix, the A matrix, the B matrix, and some gain constants. Okay, so we have the identity matrix, and we subtract the A matrix and add the multiplication of B that was initially obtained by the state space model as A, and with that multiplication we can make some operations, and then finally reach to the value of K and some K's. In this case, this is 1K and this is another K. Okay, and with that new information, we can now perform a simulation in MATLAB. We have the A matrix, the B matrix, and the C matrix, and in this case our D matrix is 0 because we have nothing before the initial conditions. In this case, we have an instruction of MATLAB that obtains the value of K that will be some gain modifications in order to make some like a compensator without a compensator. So now we define the instruction of the closed loop as a state space model with these parameters. So now we define the prefilter just like I mentioned before with the parameters of C over S plus C, and we perform the multiplication in order to the prefilter be before the closed loop system, and then we perform a step input simulation to see what happens with the graph, and we just run this program and we will have some response.